One way that we can make carbon-carbon bonds fairly easily is through an alkylation reaction, and specifically an alkylation at the alpha carbon to a carbonyl. This reaction can be done with any number of different carbonyls, but requires two basic steps. One is the formation of an enolate with base, and then the second is the addition of an alkyl halide. Now, what's nice about this reaction is that the main piece of this reaction, the second step, the actual alkylation, is likely at this point not a new reaction. And that's because it's really just the same reaction as one you've seen many times before. If you're familiar with the SN2 reaction, then this second step, the alkylation, follows the exact same principles and guidelines of an SN2 because that's basically what it is. The enolate is our nucleophile, and whatever we use with that, the alkyl halide or whatever alkyl group that has a leaving group on it, is our electrophile. So if we're talking about the mechanism of this reaction, basically two steps. One is the addition of base to form an enolate. Now, if the carbonyl you're using, such as this one here, is not symmetric, then the choice of base that we use will control whether we form an enolate at the carbon I've highlighted in green or at the carbon that I've highlighted in orange. And just to briefly review what that difference would be, the one I've highlighted in green, if we remove that hydrogen, our mechanism will look like this, and we form the kinetic or less substituted enolate. However, if we remove a hydrogen at the more substituted carbon, our mechanism will look exactly the same, just using a different hydrogen, but we produce what's known as the thermodynamic enolate. And how do we control that? Again, typically it's through the choice of base that you use. To form the kinetic enolate, you usually use a very strong base with an aprotic solvent. That makes your deprotonation irreversible, and so the one that happens faster, the kinetic enolate, will stay. If, however, you use a weaker base, and the term weaker is relative here, it still has to be strong enough to remove that alpha hydrogen, but if you use a weaker base and a protic solvent, at that point, the reaction will equilibrate and eventually give you the more stable or thermodynamic enolate. Regardless of which one you formed, the actual alkylation process will look the same. And so I've chosen here our thermodynamic enolate, but as I said, it doesn't really matter which one we chose. And we add an alkyl halide to it. Carbonyl reforms, and these pi electrons attack the carbon, kick out the leaving group. And so as we can see, we've formed this new carbon-carbon bond at the alpha carbon. Most important things to keep in mind with this reaction is, as we said, this step is an SN2. And an enolate, while we're using it here as a nucleophile, can certainly function as a base. And so all of the same principles that we're familiar with for SN2 reactions have to apply here. And that's especially true when looking at the electrophile. Elimination does still compete here. So you need to pay attention to that with the electrophiles that you use. And since this is an SN2, basically limited to primary and some secondary leaving groups.